Welcome to this week's episode of Petroleum Geology 101. On today's installment, we will be having a look at unconformity petroleum traps, their formation, structure, and significance. We will also present two case studies which feature some of the largest producing oil fields in North America. Lavorsen classically defined petroleum trap as the place where oil and/or gas are barred from further movement, and consist of subsurface features which are capable of receiving and storing hydrocarbons. A viable trap must contain two fundamental components: a reservoir rock, which is both porous and permeable, allowing for hydrocarbon accumulation, and an impermeable seal, which keeps the hydrocarbons from migrating out of the trap. There are two major types of petroleum traps: structural and stratigraphic. Often, traps can be classified as a combination of the two. Stratigraphic traps can be further subdivided into depositional pinch-out, unconformity-related, and diagenetic. Today, we will focus on unconformity-related traps. In unconformity traps, unconformities catalyze contacts between porous reservoirs and impermeable seals. They are often found in relation to mid to late Cretaceous age worldwide unconformities. They are classified into two major categories: sub-unconformity traps and supra-unconformity traps. Sub-unconformity traps, as the name implies, occur beneath an unconformity. Porous and permeable beds are typically overlain by an impermeable layer. Some examples include traps that have resulted from the truncation of tilted strata. The unconformity surface is highlighted in red. Or traps associated with incised valleys or canyons. Supra-unconformity traps overlie unconformities. Some common examples include on-lap onto regional unconformities, and also reservoir deposition within incised valleys of canyons. This animation shows the formation of a sub-unconformity petroleum trap. Initially, future reservoir rocks are deposited. As deposition ceases and uplift and erosion occurs, the unconformity surface is created. Eventually, deposition continues and an impermeable layer overlies the unconformity surface. Petroleum migration then occurs up towards the unconformity surface. Ideally, these accumulations can then be exploited for economic benefit. The Prudhoe Bay Field in Alaska is the largest oil field in North America. Oil was first discovered in 1968 and production began in 1969. Original oil in place was estimated to be about 25 billion barrels. It is located on Alaska's North Slope and covers an area of over 860 square kilometers. It is about 1,100 kilometers west of the United States-Canadian border. It is bounded to the south by the Brooks Range-Herald Arch orogenic belt and offshore to the north by the passive continental margin of the Canadian Basin. The region is interpreted as an ancient fluvial-dominated delta. The alluvial plain graded into a delta plain cut by distributary channels that fed distributary mouthbars on the broad delta front. River dominance is inferred from the abundance of unidirectional current structures and soft sediment deformation combined with the absence of wave-formed tidal and biogenic structures. Delta successions are typified by coarsening upward successions of sandstone and conglomerate deposits. The Franklinian sequence mostly includes Devonian and older sedimentary rocks that are buried and metamorphosed beyond thermal stage of oil preservation. The main production area is located in the Mississippian Triassic Ellsmerian sequence. It consists of carbonate and shallow marine to non-marine siliciclastic deposits and mostly continental shelf deposits. The Jurassic and Lower Cretaceous Beaufortian sequence consists of locally derived rift deposits. It is dominated by multiple unconformities and normal faulting. Deposition of the thick Brookian sequence provided the overburden necessary for the thermal maturation of the petroleum source rocks in the Ellsmerian sequence. Petroleum in the Prudhoe Bay field is attributed mostly to three principal sources from chemometric and biomarker analyses. 1. Carbonate-rich Middle Upper Triassic Schublick Formation. 2. The clay-rich Cretaceous Hughes Shale. And 3. The Kingac Shale. The reservoir rocks in the Prudhoe Bay field are mostly composed of Permian to Triassic sandstone and conglomerate deposits. As noted earlier, the depositional environment was interpreted to be a fluvial-dominated delta. Productive intervals are overlain by extensive floodplain deposits, which are mostly mudstones and siltstones, making up the entrapping facies. The reservoir porosity varies between 20 and 24%, and permeability ranges from 300 millidarcies to several darcies. The average reservoir depth is 2,500 meters, and the average formation thickness is 100 to 200 meters. The petroleum in Prudhoe Bay is largely held in place by an unconformity trap. The unconformity resulted from uplift and erosion along the rift margin, which created a regional lower Cretaceous unconformity. The unconformity truncates older rocks to the north and created a pathway for the migration of hydrocarbons and for recharging multiple sub-unconformity reservoirs. Cretaceous mudstones overlying the unconformity serve as a seal. Stratigraphic distributions of oil samples were used for the reconstruction of petroleum migration history along the north slope. Early burial of west to east propagating sediments resulted in the generation of petroleum in the Schublick Formation. It also included input from the shallower Kingac Shale and Hughes source rock. Petroleum produced from this source area migrated up-dip northeastward into fluvio-deltaic sandstones in the Ivashak Formation in the Prudhoe Bay field. Subsequent uplift in the west and continuous burial in the east resulted in the generation of petroleum in the Hughes Shale source rock in the east. The Shubiak and Kingac Shale formations are notably absent to the east of the Prudhoe Bay due to erosional truncation by the lower Cretaceous unconformity. The westward up-dip migration of oil along the LCU resulted in mixing with previous emplaced, dominantly Shublick Formation oil in the Prudhoe Bay. Along the north slope, oil resources are dominated by heavy oil, with APIs ranging from 14 to 22 degrees. The central region has an API gravity of 35 degrees, and the east is mostly dominated by gas condensate. Of the original 25 billion barrels of oil in place, about 11.3 billion barrels have been removed at this point. We now go to East Texas. The East Texas oil field was discovered in 1930, and production started soon after. There was originally estimated to have been nearly 7 billion barrels of oil in place. The East Texas field is a prolific oil field that encompasses 542 square kilometers in parts of 4 counties in eastern Texas. It lies along the western flank of the Sabine Uplift, an anticlinorium situated along the Texas-Louisiana border. The field is located on the eastern edge of the East Texas Basin, a structural embayment of the Gulf Coast Basin, from which it is separated by a monocline known as the Angelina Caldwell Flexure. It is bordered to the north and to the west by the Mexia-Talco Fault System. The 3 major stratigraphic units present in the East Texas field are the high-stand deltaic reservoir sandstones and overlying incised valley fill, and bed-load fluvial deposits of the Upper Cretaceous Woodbine group, which are overlain by shales and limestones of the Eagle Ford group, and truncated by an angular unconformity and overlain by the Austin Chalk. The Upper Cretaceous Eagle Ford group is the source of hydrocarbons in the East Texas field. It comprises of 2 stratigraphic units, a lower overall transgressive package of marine, laminated shales with minor bioturbation and limited fauna overlain by an upper regressive unit made up of shale, limestone, and calcareous quartzo siltstones that exhibit a more diverse faunal assemblage. The Eagle Ford group began producing oil and gas in the early Miocene, attaining peak generation around 20 million years ago. Total organic carbon values range from 1 to almost 10%, and both Type 2 and Type 3 kerogen were generated, with oil produced by the lower unit and gas from the upper unit respectively. Oil migration was strongly water-driven, took place laterally along the base of the Austin Unconformity within the Woodbine group of sandstones, unable to penetrate and thus becoming trapped. The Woodbine group represents an overall coarsening upward succession that comprises of pro-delta, delta front, delta plane, and interdistributary channel facies. The finer-grained reservoir sandstones were deposited during a high-stand systems tract, forming the deltaic succession. They are composed of calcareous laminated mudstones, interbedded with very fine-grained sandstones and coarse-grained siltstones. The uppermost part of the succession is made up of medium to coarse-grained gravelly sandstone interbedded with very fine-grained sandstones and minor siltstones that represent non-marine, bed-load, fluvial incised valley fill deposits of the low-stand systems tract. The porosity of the reservoir is consistently high throughout the East Texas field, averaging about 25.2% with an average permeability of 486 millidarcies. Primary hydrocarbon accumulation in the field occurs in the Woodbine group sandstones that thin and pinch out eastward against the western flank of the Sabine Uplift. During deposition of the Woodbine group, the Sabine Uplift was active, which exposed the strata to tilting and erosion. This resulted in the formation of the base of Austin angular unconformity. Calcareous siltstones of the transgressive Austin Chalk were then deposited on top of the truncated Woodbine sandstones, forming the impermeable seal and the trap mechanism. The East Texas oil field features an API gravity of 38. Of the initial 7 billion estimated barrels in place, about 5.5 billion barrels have been extracted. Production is ongoing, and enhanced oil recovery methods have become popular. Thank you very much for joining us on this week's episode. Until next time.